Hello, everybody. My name is Julian Melo. I'm from Colombia. Came here to do my master's at Laurentian, and it seems I'm the only master's student presenting today, so I'm excited. So I'm presenting the trace element content of gold across Ontario's gold deposits. So first, I want to thank the government, industry, and academic partners in this study. It was possible because of the involvement of the Ontario Geological Survey, the Royal Ontario Museum, and a bunch of companies that donated samples to the project. So you can see all those nice companies that work with us. So I'm presenting today overview of the gold fingerprinting project. That it's the large project where I'm working with. Sample coverage, some of the methodology that's really important because we developed the methodology for the acquisition of the data in the gold because little work has been done on this. Some of the results that we obtained in different scales, including the province scale. I'll show you a case of study in the AVTV as a district scale, and also a case of study in the Pardo project that I'll show later. Discussion of those results, the implications, and some conclusions. So first, the big research questions that we have in this project are what elements are truly associated with the native gold. That's because normally we have studied gold through proxies like quartz or other minerals that are associated with the gold, but not truly the native gold. Also, the other question is what can gold's geochemical signatures tell us about the ore forming processes and the variable gold endowment that we have specifically here in Ontario for my talk, but the project will look at other different scales. How will this help others? Well, the method development that I will talk later. We will produce gold geochemistry maps and a freely available database of Ontario specifically here, but we'll include more data in the future. For industry, will be very useful for exploration targeting and metallurgical information. And in other aspects of science, apart from geology, like forensics or artifact research, like tracing gold, coinage, and other artifacts. So we have 299 samples just for laser ablation. That will be the most important technique that we use, but we have 308 samples in total. That difference is because we could do a microprobe, of course, in all of them, but only a laser only in 299. From 77 deposits, only 70 with laser. Of the most important deposits and occurrences across Ontario from 12 of the most important metallogenic belts and mining camps. So that will include the Red Lake with very important deposits like all the Red Lake camp, the Great Bear deposit that we saw earlier, deposits in the Confederation Lake, in the Pickle Lake. I had to group these mines in Western Ontario. They are not really close to each other, and we'll see that they don't behave similarly, but they're in Western Ontario. Very important deposits in the Geraldton, Bermore mining camp, in the Wawa sub-province, including the Wawa Gold Corridor and the Island Gold Deposit. Very important deposits all across the Abitibi, both over the Porcupine Destor Deformation Zone and the Lardell Lake Cadillac. Deposits in the Southern Province associated, for example, to the Sudbury Igneous Complex as Vermilion Crystal, and the Pardo deposit that we'll see later, and deposits in the Grenville area, also one in the Temagami Greenstone Belt. So I'm going to show the sample coverage in the Abitibi because we will see later the Abitibi as a case of study. We have 126 samples from 27 deposits, including present and past producers, I divided the samples between the AVTV PD and AVTV LLC, depending on the location of these deposits associated with the Porcupine Destor or the Larder Lake Cadillac deformation zone. We can see that we have a very good coverage of those deposits. So first, I'll talk more about the methodology. The first step, of course, was taking the gold from the samples and mounting them in epoxy box. We can see here, for example, one of those boxes with the gold grains. They are big, like between 1-2 millimeters wide. After mounting them in this epoxy box, we did SEM and microprobe data acquisition. We observed that the big majority of grains are homogeneous. We only have 2 or 3 gold grains that have this kind of micro veinlets with a different gold composition, but the vast majority of them are very homogeneous in the major and trace elements, as we will see later. Mostly quartz, carbonate, pyrite, and chalcopyrite are associated with the gold, and associated meaning that they are in the borders or in the same sample, but as inclusions in the gold itself, they tend to be inclusion-free, but when we get the inclusions, they are mostly tellurites like altite, calaverite, and hesite, as we can see here from a sample from the Macassa mine in the Larder Lake Cadillac zone. Also arsenopyrite, pyrite, pyrrhotite, and galena. Also, this step was very important because the microprobe data acquisition was used to control the data that we got from laser ablation. So the next step was the LA ICP-MS data acquisition. We had 10 spots in each sample where size permitted. We had to reduce a little bit in some samples, but in the vast majority there are 10 spots. Randomly distributed, trying to avoid inclusion so that we get the data from the gold and not from other phases. We acquired data during the methodology development. We got to a specific or a methodology of what the laser have to do. And the data processing was done in IOLITE software, where we translated the time resolved spectra into quantitative data. We did also QA/QC on this data, and the quality assurance was done before, of course, getting the data. We did a lot of polishing tests, as we can see here, to get the best polishing in the gold to avoid contamination. We did those tests on those contamination, including other metals like silver, copper, or a compound of mercury telluride. We also defined that the best spot to acquire the data was 50 micrometers. The best ablation fluence was 5 joules per centimeter square. And we developed an in-house reference material, a gold sample from the Preston mine that we used also to compare to our data and see that it was good. In the quality control, we had limit of detections between 0.001 and 1 ppm for the majority of elements. We had a very good agreement between the microprobe data and the laser ablation for the major and minor elements, including gold, silver, copper, and mercury. We had a good accuracy and precision, below 15%. However, we couldn't quantify selenium and platinum because, as we can see here, they are not in agreement with the reference materials. Interferences were tested using pure metals and different collision chamber settings in the ICP-MS. We observed that we had an interference with palladium, for example, that we corrected for. Also, we had some interference with tellurium that we corrected for. And we have a very high background noise for silicon, sulfur, phosphorus, and calcium that did not permit their quantification, but we are not too worried about those specific elements. So getting into the results, the first thing that we obtained was the gold fineness, because this could be obtained just with the microprobe data. The gold fineness is just a description of the natural content of gold, the element in native gold as mineral. We can observe that there are not big differences across the province. You can see that all the gold in Ontario varies between a minimum of 750 to a maximum of 1,000. That's a very pure gold. Again, we observe that the grains are very homogeneous. There are no zonation in the grains. And as a first approach, we observe that there is a very strong control on fineness that appears to be proximal to higher grade metamorphism or deformation zones, and that made us think about a natural refinement of the gold that I'll talk about later. Also, because I will get more into the Abitibi, in the fineness we observed that the Lardell Lake Cadillac samples are different in fineness than the Porcupine Destor Fault Zone. Remind that we are already observing differences in gold between those two zones. That was for the major and mineral elements. Getting more into the trace element side of the things, the 8 elements that were most commonly found, that means that it's about the 60% of the samples measured were, of course, gold, silver, but also copper, mercury, antimony, bismuth, palladium, and cadmium. Silver and copper show a linear relationship with gold that's observed very often from different authors because there's alloy between the gold, silver, and copper. But it's also very weak with mercury, as expected. However, the other elements that are in the gold, I'm just putting here antimony as an example, but it's the same for the others. They vary despite the gold content, and that's why these other elements are very useful to show spatial variations at different scales. In a province scale, we'll start from big scale to a more small scale. We are seeing a systematical variation in antimony across the province, specifically across the Superior Province. For example, we are seeing that the antimony content in native gold is high in Northwest Ontario, including the Red Lake, Pickle Lake, mining camps. Something starts to decrease a little bit towards the Geraldton, Vermore, towards Wawa, and in the Abitibi tends to be very low, a little bit higher in the Abitibi Porcupine Destor than in the Lardell Lake Cadillac. We can see something more or less similar in mercury, but the other way around. We are seeing high contents of mercury in the gold in the Abitibi zone that starts to decrease towards the northwest, even though we have some samples with high mercury in the Red Lake area. But for the rest of mining camps, we are seeing that decrease towards the northwest. Something similar happens with cadmium, shows a similar trend as antimony. We're seeing a high content of cadmium towards the northwest, but low contents towards the southeast, including the Abitibi and Swayze areas. And the palladium doesn't show a systematic variation as the other elements, But as expected, we have a high palladium for those deposits near Sudbury, including the Vermilion and crystal deposits that are associated to the Sudbury igneous complex. But it's also very interesting that it's high in deposits like Upper Beaver and Cote Gold. That made us think that maybe it's associated with if you are familiar with Cote and Upper Beaver, they are interpreted as associated with magmatism. So that made us think that maybe palladium is coming in play in something like that, but something that we'll have to look better. Going into the district scale, so I'll show AVTV as a case of study. As you remember, we were seeing those differences between the gold in the Larder Lake Cadillac and the Porcupine Destor in major and minor elements, but that will also be true for trace elements. For example, in the antimony, we are seeing that the samples in the Porcupine Destor have higher antimony than those in the Larder Lake. Same for cadmium. It's the same trend, but it's the opposite for copper. We're having higher copper content in the Larder Lake than in the Porcupine Destor. This can be explained because of the gold fineness is higher in the Larder Lake Cadillac than in the Porcupine Destor. And as we saw, the copper is directly correlated with the gold content. But still, we can see those differences, and that can be helpful in the AVTV at least. Going into a smaller scale, this is the Pardo project. This is a paleoplacer deposit to the northeast of Sudbury. We did analysis of detrital grains and a population of in situ grains, vein occurrences that is up in the paleoflow. And we can observe that, we have this in situ vein occurrence that is the green one, and we have three populations of the detrital grains, the blue, red, and pink populations. And we can see that the blue and pink have very similar trace element content and ratios than the in situ occurrences, but we have a very different population that it's this red one that have a high content of uranium and palladium, but very low in other elements. So that makes us think that there are at least two different populations in this paleoplacer. That can mean that maybe there are two different sources. We're not completely sure of that, but at least we can see that in situ vein occurrence can be the source for those blue, and at least for the blue, the pink has some more or less different signature that maybe has combined grains between these two populations, but we're not completely sure. For the red ones, the uranium content is high. Maybe we are having some uraninite inclusions that are coming into play in this gold, but the grains were small, so we think that it's part of the gold, but we have to make sure of that. So for the discussion, because we were observing these different variations of trace elements across the province, then the different mining camps started to show some trends, and we came with this plot, the antimony over copper against mercury over cadmium, and that proved useful to differentiate that the gold from different mining camps had different microchemical signatures or trace element signatures in the gold. For example, the AVTV Larder Lake in dark blue plot very different than those samples from Red Lake. It's same for more or less the Geraldton Barrymore. The Wawa samples tend to plot very low in the diagram. The AVT porcupine dester is the one that has the broader signature in the trace elements. We can see we have some overlap, especially with the AVT Villar del Lake, and there are some samples from Dome that has from Dome mine that has high antimony content, and it's overlapping with the Red Lake area. But still, as I said, this has not been a lot before, and we are seeing some very promising results. The first thing that comes to our attention when we're seeing these trends is that the trace element content in the native gold is completely independent of the deposit type or local host rock that is hosting the deposit or the mineralization in the area. And it's more associated with these big mining camps or metallogenic camps and belts. This can be explained by a possible control due to craton to district scale processes. I came with two possibilities. One is because of the nature of the samples, we cannot be completely sure if the gold is primary or secondary, because the majority of the samples were obtained through the Royal Ontario Museum, and it wasn't like collected from us in situ to determine if it was like in a specific event. So we have these two possibilities. If the gold is primary, it will be showing that the gold in that specific mining camp, say AVT Villar Lake or Red Lake, have a similar metal source that can be, and the underlying crust in metamorphic devolatilization, but because we have several different type of deposits in an area, there should be another also source like the subcontinental lithospheric mantle or the magmas that are coming into play, and those sources should be homogenized in a conduit or in a system, and we have to stop thinking just like individual deposits and more like mineral systems in an area. So that could be true. For example, to think about those metal sources that are giving this signature, I have highlighted the camps that have mostly underlying Neoarchean crust, like the Abitibi porcupine, Swayze, Temagami, mostly Wawa, that's why we have both colors. And I have highlighted in red the underlying Mesoarchean crusts. You can see that those with Mesoarchean crust tend to plot towards the right with higher antimony, as we saw in the trends in the previous diagrams. And the other camps tend to plot more towards the left side of the plot. So that maybe can be one of the possibilities on why we have these different signatures. Also, what comes to our attention is the Abitibi Villar Lake, Swayze, and Temagami samples have have a similar signature in trace elements. That maybe is possible because we have similar geological processes in these camps and areas. We have a broader signature for the porcupine dester that can mean that it's sourcing different things or more things. That's one of the possibilities. The second possibility is if the gold is secondary. And what I mean with that the gold is secondary is that it has been remobilized mostly. As we have seen in previous talks, the remobilization of gold is a concept that has been or has gained more fame during the last years, and there's more and more evidence about this process. For example, I have modified from Hasty and others in 2020 this diagram. This was developed for the Swayze Greenstone Belt, but observing other authors is more or less the same through different deposits. And what we have is a remobilization of gold that was initially in pyrite and arsenium pyrite, that it's taken out from the pyrite during coupled dissolution or precipitation processes, and low melting chalcophile elements that are also in that pyrite are getting out of it and helping the gold to remobilize and reconcentrate in other parts of the deposit. So that those elements, those low melting chalcophile elements, are mercury, antimony, bismuth, tellurium, and cadmium, and that's the elements that we are seeing in the gold. So that will make a lot of sense that the remobilized gold that is associated to these fluid-mediated melts that's why we have that fingerprint. But if this is the case, still we are seeing that there is a district scale event that is giving the fingerprint to the gold. So this remobilization should be something that is happening the same across the camp or the mining area. The last concept that I want to show you is the natural refinement of the gold. This is something that we observed in our samples, that there are elemental depletion over 975 fineness. That means above 97% more or less of gold content in the native gold. And it seems there is a strong control on this fineness proximal to high-grade metamorphism and deformation. And I have an example of that specifically from the Madsen mine. The Madsen mine is it's a mine in the Red Lake area that has gone at least under two metamorphic events, an amphibolated fascist regional metamorphism and a contact metamorphism. And we can see that those, this is the same diagram that I showed you before, but I have taken out all the other samples from the other areas. And I'm showing the Red Lake samples areas, the Red Lake samples, and the Madsen samples tend to plot away from that area. And it's showing that there is a depletion in the elements in that mine. So this is a concept that we are looking more into it, but still we can see that it happens with copper, mercury, and this is a sum of all the other trace elements, and we can see that still we have that depletion in trace elements and minor elements in the native gold. So implications of this data, implications in the ore forming processes, we can see that there is a regional metallogenic control rather than a deposit type control or individual deposit type control. We can see that there is a role of deformation, temperature, and metamorphism in the gold fineness. That's the natural refinement of the gold. For exploration, this is important because we can use native gold as a better indicator mineral for gold deposits, because we can now, or with this data, we can rank best pathfinders in a zone that are directly related to gold and not other associated minerals. For example, in placer or paleoplacers, we can identify if there are different sources for the gold in these kind of deposits. In forensic geology, it is possible to identify the source of a gold sample. For example, if it comes from the Red Lake that has a very different fingerprint or signature than the Larder Lake in the Abitibi. And this will be a database in the future that will be freely available, so this can have impacts on other geoscience and scientific fields that we haven't thought of or we are not aware of. Some conclusions. The methods developed in the project are robust, reliable, and reproducible, as we saw in the QA and QC. The gold, copper, mercury, antimony, bismuth, palladium, and cadmium are the elements that are commonly detected in native gold, at least in Ontario. We show that the trace element concentrations and radius are useful to fingerprint gold at different scales. We are seeing that the gold from the Abitibi porcupine Destor and the gold from the Abitibi Larder Lake is different, show differences in antimony, palladium, cadmium, and copper. The Abitibi Larder Lake, the Swayze and Temagami greenstone belts have similar trace element signatures, and that may indicate they have undergone similar geological processes. In paleoplacers, the native gold can be used to identify different gold sources. And the gold microchemical signature varies at the craton scale, but is very consistent at the camp scale. So this suggests, as I said, that the district scale processes are common to this gold camp mineralization. And lastly, the gold can undergo a natural refinement with the increasing temperature or pressures, as we saw with the elemental depletion and the homogenization of the samples. Thank you so much. Thank you to my supervisors, Dr. Harold Gibson and Dr. Evan Hesty, and the industry that donated samples to make this project possible.